Good morning or good afternoon. Welcome to another Connection Wednesdays, our regular online live training focused on the design and code check of steel structures in StatiCa connection software. Today we have another very nice example from our customer. But before we start, let me just mention some things. My name is Jana, and together with my colleague Adam, we will again show you two examples. The first one, the customer project, and in the end, we will have a look at our help desk highlight example. And as usual, you are muted by default, but if you want to ask some questions, please feel free to use the questions panel in GoToWebinar application. We will answer them during the webinar, and also if we don't manage to answer them all, we will write you an email after the webinar. The customer project that Adam will present in a while is a connection from the exterior facade of Barcelona Arts Hotel, and help desk highlight will be focused on a comparison between hand calculation and idea StatiCa. In the end, we will try to answer some of your questions. And now let me pass the presenter to Adam, who is, I think, now prepared to tell you something more about the help desk, about the customer project.
Hello. Hello to everybody. I'm just taking the presenter right now and jumping into the presentation. Hope you can see that. So hope you're fine. Nice to see you again here. And today we'll take a look at one joint from the Barcelona Arts Hotel, the magnificent skyscraper from Barcelona coast. And this is really an iconic building in Barcelona. This is a little bit about the history of this building. It's there for about more than 20 years. It was built for the Olympics in Barcelona. It was 1994, I believe. And the design or the architecture was done by one American architect in cooperation with the local architects. And yeah, so I believe they made a change the face of the Barcelona coast with this marvelous steel structure with the outside supporting structure on the facade. Unusual, but for me, very nice solution. So about this project, as you can see some pictures here, just to make you feel how it is to be there inside. Maybe one day we meet each other there. But we got this sample or this model from our partners in Spain, which is company Construsoft Spain. They are located in Barcelona, and they have this this joint model in idea StatiCa as their example project that they show. Of course, in that time, in these early 90s, there was yet no idea StatiCa on the market. So they struggled, I believe, a lot designing this this construction and these joints, and we will see how you can do such a joint in a few minutes in Idea StatiCa now. So let's do that. Let's jump to a new project. So I will choose some starting topology, let's say this one, to have 4 members, and I will change the steel grade to 275. That's the material from that time that they used, and create the starting topology. And of course, I will have to do first something about the geometry. So I will first set this member to end it, and copy it to have really 4 members. That I do now. And next one will be to change the cross section. So I will add a new cross section, and that's pretty unusual for the members. So it's not in the library. So I will have to go to the general steel cross section creator or editor, and I will compose it by myself. So I will choose a general plate here, and I will model this cross shape cross section. So the thickness is 12 millimeters of the plate, and width 240. I have a basic plate here, and now I will add another plate, continue composing. Again, 12 millimeters, 94 of length. And what do I do now is that I will rotate it here by 90 degrees and set it to the, or assemble it. So how you do that, you use these three cells here. First one is that you say that this plate that I just created, I will connect to the first plate, number 1. And next I will say which is the master point. It is here number 8. And what is the insert point? That is here number 6. So as you can see, the master point, that's the numbers on the, let's say, base plate here, and the insert point, that's the number on the plate that we are connecting. So here it's 8 and 6. And now I just copy that and do the upper part of the cross section. So now I'll change the master point to 2 and insert point to number 4. And we can check if it is working right. If we go to results, and we can see the stresses distribution on the cross section, and all is looking fine. So I can just click OK, close that, and I have the cross section assigned. I will just move this member to above 1 meter and do the same for the rest of the members. So like this. Okay, so that's for the geometry. And next we go to loads. I will turn on the equilibrium. So I'm able to load all the members now, and we have just one set of maximum normal forces here in the joint or in the construction. So, and that is minus 800 And so this is just one envelope combination of normal forces, just to demonstrate the model. Okay, that's for the loads, and we'll start with the operations. First thing I will do is to add the main plate, the star-shaped plate. I will do that by the stiffening plate operation. And here I will change the shape from rectangular to polygon, and I will import a DXF. So I have this file where that's the DXF of the shape of the plate, as you can see here. So what I do now, I just click on one of the lines here in the picture, click consecutive, all is colored in red. I'll click outline, that creates the plate actually, and I click OK. And that's it. I got a plate in a place, just that it's rotated, but no problem. I will modify it like this. Okay, that's in place, and we can continue with the stiffening plates or the cross along the star plate. So again, I will use a lot of stiffening plates now. So let's do that. This will be thickness of 12 millimeters. And if I just jump back, because I forgot to change the thickness here as well for the star plate. So 12 millimeters of thick. And now the plate dimensions of the stiffening plate are like this. As you can see, it's in the place. And the origin will be on plate, on this stiffening plate, and in the rear side. And the last thing I do is change the weld thickness and set the double fillet welds. Good. Now I will use a lot of copies and modify these copies. So let's do that. Copy, set to front. That's in place. Okay. I will make another copy to do the perpendicular parts of the cross. So I will rotate it by 90 degrees, delete this, and that's it. Now another copy, minus 90 degrees in place, another copy, front position, another copy of this, plus 90. Okay, so stiffening plates in place. Now I have to weld this all together here in this joint of the stiffening plate. So for that I will use operation cut of plate and simply choose which plate I want to cut, by which plate I want to cut, and set the thickness of welds to 6 millimeters double fillet. And now again, I will just copy this for the other three. So I'll choose this one now. This is already chosen, but I have to change the surface from the upper one to the lower one from this point of view. Welds are in position, and I do the same for this plate here. Change the position, and again another copy for this one and the minus surface. Okay, so this is already looking like something. I will continue with connecting these two members. Now there is one modification from the original joint that's in place in Barcelona, because we want to show another possibility how to connect such a member to such a shaped plate, and that is a stop. I'll choose the bolts. So the stop operation works like this. Creates two end plates, bolt assembly, and welds to both connected members and plates. And we can modify this slightly by changing the position and thickness like this. And of course, changing the position of bolt, minus 35, minus 50. So we'll add some more. And of course, we'll change the weld size, put it on both sides of the connection like this. And we can turn off this weld because there is no use for that. We've got just flanges here. So this is one type of connection that's possible to use there. That's our original or our invention, how to modify such a design. I'll just copy this simply and set it for the M4 member. All right, and now I will do another type, the real one that's in place to these two. And that's now a little bit more laborious, but don't worry. We've got a few more minutes to do that. So I will use now the splices, as you could see on the pictures. So let's do the splice operation. And again, just simply choose a plate, change the, oh sorry, that's thickness, 12 millimeters, of course, and change the size, 300. And now I have to cut it here to have it only on one side. I will use minus offset here, and that will be of minus 100. Okay. Of course, place the bolts into positions, 40, 55 by 4. And we've got this bolted splice. And I will just check this backing plate option to have the backing plate there as well. Good. Now I will copy this and use it for this size, for this side of the member. And for that, I will use this trick because it's still the same member, but you have to change the offsets. Yeah, from offset number one, from one side to another side. And you got it cut. And of course, the position of bolts. So I just add minus here, and I got it on the other side as well. Good. Now, of course, I need some bolts here as well, but for that I need to use another operation because this splice plate works just for one member and the created plate, created splice. So I will use the bolt grit operation, and I will say 3 items because it's 3 plates here. So let's pick them by this arrow function, just 1, 2, and the third one. And again, the same bolt position like on the one member. Good. And again, of course, I will copy this and set for the other side of the member. And of course, change the position here. Good. So that's the horizontal splice, and now the vertical. I will again use the favorite feature of IDEA StatiCa, and that's the copy function of operations. So change the member here and change the, of course, the size of the splice, and that is now once more. Okay, that is now 0 here. We got the splice in place, and just cut it by -20. Okay, and change the positions. If I take a look, by 0 it's here. I want to move it a little bit upwards. Let's do that. Good. Again, another copy of copy. So again, I change this one, change the parts of the member, and change the position of the bolts. Good, and now the last bolt grid, I will take this one and copy it, choose the plate, 1, 2, 3, and change the bolt position, right in place, and last one like this. Okay, and now here 10. Good, so this was quite a labor, but with these splices, with all the plates and the special shape, there is no other way for now how to do that. But still, we're quite in good time. Now, for the other part, or the other end, I will just copy all the operations that I did here for this member and this plate, just set them right, and we get the same here. And I will skip that and skip the calculation because with this quite complex joint, it takes a few minutes, about 2 minutes, which we don't want to spend here looking at the calculation being performed. So I will just open the model already calculated that I prepared. So we can see here all screen. That means we passed the code checks. We can read the overall results here in the 3D scene. That's good. And if we would like to browse the results, we can do that, of course. We can take a look on the plastic strain and how the mesh was created. All is looking good. If I take a look at the bolt forces, yeah, something what I would await. Let's take a look at this one, for example. We have some normal forces here, but that's because of the finite element calculation, because of the deformation of these plates. We have some extra normal, small normal forces, but the main code check here is for the shear force, of course. So that's how it's written here. And shear about 43%. Okay, and then of course you can go to report and print that out or export to Word document and work with that. So I think that's it from my side. That was the magnificent Barcelona Arts Hotel steel joint, and now I'm giving presenter to Jana.
Okay, thank you, Adam. I tried to answer your questions, but there are quite a lot of them, but most of them repeat. So I hope we will try. We will answer them during the rest of the webinar. Now let me show you the help desk highlight presentation, and so this time we will speak about a comparison between hand calculation and idea StatiCa results when calculating the stress in the weld. So our customer was curious about different results that he got from his Excel table, and basically he asked about the sorry, I have to open the prepared equations. He asked about the parallel shear stress in weld. So he had a connection like this. Let me just show you. Let me just show you the structure. So in the beginning, he had a connection like this. Only a simple plate connected to a column by a double fillet weld, and if he ran the calculation, he got some result of the tau parallel, which is the parallel shear stress parallel to weld axis. And in his hand calculation, he got a totally different result. Our value was about 12, and his about, let's say, 3 megapascals. And so, what can be the source of such difference in those results? So first, let's have a look at the formula. Into the formula, we have shear force, and then if it's double fillet weld, we divide it by 2 times the length of the weld, and also in case of Eurocode, it's the throat thickness of the weld. If you calculate according to American or different codes, you have to recalculate from the leg size, but this formula corresponds to Eurocode. And of course, we have to have a look if in the model we have only the shear force, which means we will have a look at the load effects. We have some shear force here in the table, but if we switch the model to wireframe, you can see that, of course, the shear force is in the node, and as there is a zero moment, which is not really realistic for such type of connection, because if it's welded, we suppose that there will be also some moment. But now we can see that where there is the weld, at the spot of the weld, we have also some bending moment, and this moment also influences the distribution of stress. So if we want to simplify, just for this example, we will shift the shear force a little bit to the right. So now if we display the model, so this is the position of the weld, and if we turn on the wireframe model, we can see that there is zero moment at the now. So we can calculate it in a more clear way. Okay, so but still there is a difference. in results. So let's have a look again on the stress in the weld. And you can see in the bottom right corner the distribution of this equivalent stress along the weld length. And you can see that in this CB-FEM model, it's not one value. In the simplified formula from the code, there is only one value, but in reality, the stress is distributed somehow. So probably the value from Eurocode would equal to the average value from this figure if we make an average from these values. So if we want to have some really nice example of such connection, I will just change a little bit the load so that we will get to the plastic stress distribution. So I will increase the force, and also I will increase the thickness of the plate so that the plate will survive. And let's little bit lower the thickness of weld. Okay. And now I will recalculate. And we will see that now, as we are in the plastic region, the stress is really equal along the weld, and the value now it's about 251 megapascals, which I prepared just a little equation. If I substitute it into the equation from Eurocode, you can see that we are just at the value from this formula. So this formula supposes that the stress distribution is equal. In the first example, you can see that the formula gave us about 21 megapascals, and we had a very different value. So anytime you get some different results from hand calculations and our models, the main reason is that it's FEM-based calculations, and usually formulas from codes suppose some simplified models. Okay, so and I think we have time just for one or two questions.
There was one question about the end plate on a tubular members. So if we support curved end plates that you connect to a tube. So unfortunately for now we don't. That would be something like this, but this end plate would be curved around this tube. So we don't have this for now, but I believe in future you will find it here as well.
Okay. So, I have also one question. It was regarding the DXF import of plate that you showed, and somebody had problems with it. So we maybe can just note what are the most usual sources of problems when you try to import plate from AutoCAD. So I think, Adam, it's usually that you have to disconnect all entities, right? Am I right?
Yes.
Usually you have some objects in AutoCAD, so please try to disconnect to really simple.
Yes, explode. If you want to import in DXF, it has to be in the most simple form of it. So if you have it in AutoCAD, for example, as an object, you have to explode it out to just simple lines, and then you're able to import it. Another error comes that you have to close the file, the DXF file, before you import it, because when it's opened, you cannot read it with IDEA. So
yeah. And maybe I also know that you have to check the units. So if your drawing is in millimeters, you have to switch in the import window. What Adam showed, you have to switch to millimeters, and if you are in meters, you have to be in the same.
Yes, units. we cover this transformation during the import, so you can do that.
Yeah, and of course, I want maybe just to mention that you can also import not only plates, but also different openings, different shapes of openings. It's also possible. Okay, so I guess I will just make
nice end.
Nice end. Sorry. Yeah. So thank you for your time. After the webinar, we kindly ask you to fill a very short survey to give us some feedback, and maybe write us what are you interested in, so that we can prepare some other webinars about such topics. You will also, of course, get the recording of this webinar. It will be on our website and also on our YouTube channel. And if you don't have IDEA StatiCa, please go to our website and get a trial version to try it yourself. If you are curious about something regarding IDEA StatiCa, please go to our resource center, which is the best page to find any type of technical information. We also prepared many other webinars about the different topics, so this is also a good way how to find out something or maybe get some inspiration. And you are also welcome to join our next Connection Wednesdays, which is in 2 weeks on November 28th. I think at the moment you can already sign up for the webinar on our webpage under Webinars tab. And that's all. Thank you very much for your time, and I hope we'll see each other next time.
Enjoy the November. Bye bye.